welcome to the last day. We also arrived. I'm very happy to Alessandra Bernardi. She's going to speak about the dimension of Tensor Network.
Okay, so thanks, John, for this great presentation. Thanks you for being here, despite the weather, despite the time, despite the new building. Okay, so today I want to talk about this dimension of Tensor Network varieties. This is a joint work together with the former student of myself, that is Claudio De Lazzari, and Fulvio Gesmundo, that probably many of you know. So this is an overview, motivations, definition and properties, and then what we can say about dimension and further questions. So motivations, probably you have more motivations than what I say, because in this audience there are many experts. So, I mean, one motivation of studying Tensor Network is we have already seen all the talks we have seen from yesterday. So the dimension of the Hamilton space is huge, and it gets intractable quite soon. So if you have to deal with a tensor, you have to deal with a lot of entries of the tensors, and you would like to reduce the number of parameters. And apparently, Tensor Network are a good place to look at to reduce the number of parameters. And then there's this other motivation that I don't see that we have actually seen in this up to now. So let me tell you, it comes from quantum physics. That so if you want to see, if you have your tensor given like that, right? And you are interested in knowing the entanglement of the tensor and looking at just its coefficients is not clearly immediate, which is the entanglement of this tensor, right? And while for that, I mean, if they have particles and they put their particles in their lab, they kind of assume that the particle interacts between the neighborhoods. And so the entanglement is really given by the structure of the place where they put their physical particles. And this is something that apparently is well described by Tensor Network, because the network that you can use can really represent the network where you put your particles. So it's also an immediate way to encode the entanglement and see how the particles are entangled among each other. So, okay, Tensor Network has this information directly available in its description. And so let's do baby case, matrix product space. So the matrix product, if I have to multiply two matrices, A and B, and get C, the coefficients of C are obtained as we learned in the first year, not as Sasha teaches us. So this is how we do the matrix multiplication, and this can be encoded in some graph, and this is how we encode it. I mean, this is the graph that encodes matrix multiplication. So here I have one matrix, and I link this with another matrix here. And this is probably have another slide for this. Sorry. Yeah, I'll say it later. Sorry. So just here I'm still in the motivational part, and so here we can see that already the number of parameters already the matrix product state is much smaller than the number of parameters of the ambient space, and as I said, it may highlight the entanglement structure of your state. So another motivation for studying, now that work was for Tensor Network. Now I would like to say some motivation for studying dimensions of these varieties. So regarding the number of parameters, already, if you take the standard parameterization of the Tensor Network, the parameter space, it's okay. We have seen that as smaller dimension than the ambient space, but it still has two big dimensions with respect to the dimension of the Tensor Network variety. So if you're interested in parameterizing a tensor that lies in the Tensor Network variety, so the minimum number of parameters that you need is the one of the dimension of the variety. If you have a parameterization and the parameterization is a huge fiber, then you're still losing parameters, okay? So if you're really interested in reducing the number of parameters, to go and see the smallest ones, so you have to look at the dimension of the variety, not the dimension of the parameter space. And another motivation is that if you go through this and you study this fiber, the fiber of the parameterization, then what do you see in the fiber? In the fiber, you see all the, say, the parameters that give you tensors that are mapped via the tensor network variety on the same tensor network. So you see all the tensors that have the same tensor network representation, but I mean, they come from different kind of parameters. Okay, so this is a question that we have seen in this workshop sometimes. So think of the same tensor network state filled with different parameters, but at the end it gives you the same state, the same tensor network state. And that's what you see in the fiber of that parameterization. Questions so far? Okay, so now I go to the definition of the tensor network. I think that apart from the talk of Albert yesterday, we have seen the physical standard definition of tensor network variety. I would like to go through a different definition that, I mean, is different just from as far as it is formalized, because they define the same object, but let me go through it. Okay, so fix a graph. I just do this because I will have example on this, but you can fix the graph you want, okay? And then you fix some length, say M1, and some weights, say M1, M2, M3. These are called bond dimensions. And then you fix the identity matrix over here. So here you have IM1, IM3, and IM2, okay? So this identity matrix lives into CM1, tensor CM1. So let me put a CM1 over here and a CM1 over here. This is inside CM3, tensor CM3. This is inside CM2, tensor CM2. Okay, so as I define it, if I tensor everything, if I do the tensor of I and I, in this case I go from 1 to 3, this is inside the tensor product of C and I tensor, let's say, yeah, it's still C at I from 1 to 3, okay? That's what I wrote here. So they belongs, this is the tensor product of all this identity, and the index runs over the edges, okay? And so it naturally lives in the tensor product of CME, tensor CME, where E runs over the edges. But now I want to take the same tensor, so still this guy, but thinking regrouping the vector spaces, not running the indices over the edges, but running the indices over the vertices. So I just regroup them in this form here, okay? And that's what I wrote here. So it's
in Albert's talk, that was the I was the maximally entangled pair, right?
That I was the maximum.
Maximally entangled bipartite state.
The omega.
Yeah.
The omega T.
Yeah.
Yeah, you call it I. Yeah.
Yeah. Yeah, it's. So now as I wrote it here, so I tensor now over the vertices instead of the edges. And what do I tensor? I tensor all the vector space that are incident on the same vertex, such that the vertex belongs to a certain edge. Sorry, the edge contains that vertex. Sorry, the other way around. Okay. And now I call this spaces W. So W1, W2, and W3. I need to make a different picture because now it's more confusing. So it's so here I have, say, W1, W2, and W3. Okay. Okay. So, and this is my. Now this tensor regrouped in a different way. I will call it a graph tensor because it's a tensor that encodes all the notion that I had from the graph. Now I want to associate the variety, and what do? I take my graph tensor. That's the object that I just construct, and I let all the homomorphism between So the W that I just construct and the physical spaces. So the VIs are the spaces that I have here from the physical dimension. Okay, so I take all the homomorphism between from W1 to V1, etc., up to VD to WD, and I act with this by multilinear multiplication on the graph tensor. And so this orbit defines a set that we have learned from yesterday that may not be closed. So if I want to have a variety, I have to close it. If I work over the complex numbers, and I will work over the complex numbers, you can take the Zariski closure or the Euclidean closure, it doesn't matter. So the closure of the image of this variety is going to be my tensor network variety. And just to convince ourselves that it's the same definition as we... Is that one? Sorry. Yes, that is the same definition that we have seen from all the other talks. So let's do the matrix product state again. So in this case, I have only one identity matrix that goes from Cn tensor Cn. So this is just W1 tensor W2. I look at this homomorphism maps. And so I take all the, say, matrix X1 in here and the matrix X2 in here. I multilinearly multiply by the identity. This is how we write the identity. And the multilinear multiplication splits like X1 times EI and X2 acts on the second factor. And then I have the tensor product, I write the tensor product, and then I have to make the transpose. And here I actually see the matrix multiplication. Okay, so this is not a proof that these definitions are equivalent, but at least in this example they agree. And so this is. So in this case, the tensor network variety associated to that graph is a set of matrices whose rank is more or equal than the bond dimension.
What is the additional parameter n?
This is the multi-index, that encodes the dimensions of the physical state. Okay, so thanks. So this is dimension, say, n1, this is dimension n2, this is dimension n3, and n is n1, n2, n3. And with n, I will denote n1, n2, n3, the bond dimensions. Thanks. Okay? Okay, at least we have an example where the two definitions agree. And I like to use the definition I gave you. So in here it's a kind of motivation why I like this definition. So, because when you do this multilinear multiplication, the multilinear multiplication is nothing else than evaluation. Okay? So you just have to evaluate the graph tensor somewhere to see if something belongs to your tensor network variety, or at least in the open part. So this is a part for being easy, what I wrote in the second dot, but you may start with like small, if you have the question that Albert posed yesterday, so which is the smallest bond dimension such that certain state belongs to your tensor network variety, then you may start with some small n and start evaluating your graph tensor and hope to find that's the difficult part, linear maps such that your tensor gets the evaluation of the tensor of the graph tensor. I mean, they found classes where finding these evaluations is easy, but in general, this is a difficult problem, finding these edges. Okay, so let's see some properties. First of all, one may assume that all the bond dimensions are bigger than 1, otherwise you just cancel that edge. And we have learned from the beginning of this week that there are many monotonicity properties. So for example, these are multi-indices. If I pick this multi-indices being smaller than this one entry-wise, okay, then if I fix the graph and I take the bond dimension with these properties, then the two tensor network variety that I built, they are contained one into the other one. Okay, so there's the containment that goes with this n. And there is also the universality property that if you pick a connected graph, then at a certain point, by enlarging the bond dimension, you reach the whole ambient space. So you have really a filtration of the unit space. And then there are other properties. So we may always assume, so let's see this example. This is one, and if it happens that there's one bond dimension that is bigger than the product of all the other together with the physical dimension, okay, then the two tensor network variety that you build, one with this property and one with just putting an equality here instead of just a greater one, you build the same variety. Okay, so you may assume that at all vertices you don't have such a, I call an overabundant bond dimension. Okay, so that all the bond dimensions are balanced in a way. There is not one that is too big, because I mean, if it's too big, it doesn't matter. I mean, there's exactly the same variety.
Is that the same as being concise or not?
Being concise regards the V, the physical dimensions.
Yeah.
Because the tensor network variety sits inside V1, tensor V2, tensor V3. And so,
M's, yeah, sorry. Yeah, the M's are related to the V's, right, in a way, because they're upper bound kind of.
Yeah, but I'm really saying that I want none of the, I mean, these are given, right?
Yeah.
I'm not changing the physical ones here. I think that there's another notion that is more related to the conciseness. But this is clear, right? So I don't want any bond dimension be too big. Yeah. And too big is the product of all the others. So I think that this is the notion that is more related to being concise. So this definition, I brought it from Landsberg and Chi. So there are, if I pick the vertices, now they have this three definition of vertices. So a vertex V can be subcritical if it's smaller, if the physical dimension incident in that vertex is smaller or equal than the product of all the bond dimensions. Okay, is supercritical the other way around, and it's critical if it's both supercritical and critical. This, I think, is more related to being concise. And so this is one of the first results we had. So assume that you have a vertex that is supercritical. Okay, so you are in this case, one physical dimension is much bigger than the product of all the bond dimension incident there. Then if instead of putting this inequality, you put an equality here, you get a different tensor network variety. Now it's really different, but there's a clear relation between the dimension of these two varieties. So the dimension of the biggest one, the one with this inequality here, is exactly equal to the dimension of the smallest one, so where you have an equality here, plus the number of parameters that you lose if you do this game. So there's no trick, okay? So there's no exceptional things. You may, if you're interested in dimension as we were, so it's not, I mean, you can really always put an equality here, and you also know all the dimension of all those that have supercritical vertices, because I mean the dimension drops always by this number here. Okay, so there are no exception things here.
Again,
so if I have a supercritical vertex, so I have the dimension of the physical dimension is bigger or equal than the product of all the bond dimension incident there. Then, I mean, you have your tensor network variety. Now you build another tensor network variety where you replace that, that physical dimension with an equality. Okay?
So you keep the edge bond dimensions, but the physical dimensions you change.
Yeah, I change only the physical dimension incident in that vertex.
So that everything becomes critical.
Well, at least in that vertex you have the critical thing.
Oh, you're not changing
I'm just doing it once. Of course, I will do it everywhere at the end, but let's do it in one. Okay, so I change it there. Okay, and so I have two distinct tensor network varieties. Now they are different. Okay, but the dimension of the biggest one is equal to the dimension of the smallest one plus this number. And there are no exceptions. So it's sufficient that you compute all these cases instead of taking care of this, because you have to add only this number here.
Well, this is the difference between being critical and the supercriticality
Yes.
of it.
Yeah.
By what I get.
So that is essentially the dimension of the Grassmannian sort of.
Right. Exactly. So this is just a comment that studying the orbit of the tensor network of the graph state doesn't tell you anything on what is in the closure. So this is the tensor network variety, and then I take out just the image of that map. So this is the talk of yesterday. I'm not touching that area. So this is, I quoted Landsberg and Chi, but Albert had also a better, more modern reference for that. And that's, I mean, it's exactly the same thing that was said yesterday. So if there's no cycle, then the variety is closed. And otherwise, there is something in the closure. Okay, so it's not closed. And then they exhibit some tensor that are interested in there are some interest in the boundary, but this was the talk of yesterday, this one. And I'm not saying anything about this part, because the dimension is not really interested in what happened in the closure. The closure has always a smaller dimension, right? So, so what's known about dimensions now? So here I reported two results. So this one regards the matrix product state with open boundary conditions. And Buczynska, and Mikałek, they have perfect binary trees and the tensor train. I will report the result later. So this is known. And so let's go dirt our hands and see how to study this dimension. So I come from algebraic geometry, and so if I have a parametrization and I have to study the dimension of the image, the first thing that I do is what I already said. I look at the parameter space and I take out the dimension of the fiber of a generic element. Okay. So we have a parametrization, we have our graph tensor, and we have this parametrization here. So I'm interested now in the parameter space is clear the dimension that it has, and now I have to study the dimension of a general fiber. So matrix case, let's do it the matrix case. So matrix case, this is just the product of two matrices. This is how my map acts. Okay, so two matrices, I have the x1 identity, x2 transpose. Clearly, if instead of taking x1 and x2, I take x1 times an invertible matrix and x2 times the inverse of the same invertible matrix that I got, clearly I will get the same image. Okay. And this is true for matrix multiplication. This is true for all tensor or graph tensor that you can think about. And so if you collect this information together, you get that in the pre-image, you have the whole, it's called the gauge subgroup, that is the product of all the GL and E, where the bond dimensions here, in your fiber. This is something that you always have in your fiber.
And the generic point in this case means just matrix of rank m, or? Yeah.
Because I mean, matrices is easy. Here you have all the matrices are up to rank m, and so a generic one is the highest one. So the role of this group was very well known in this field. And I have to say that every time that I speak with some physicists, the idea is that it's the only thing that is in the fiber. So that's the only thing that really plays some role in controlling this dimension. And so I will call this the expected dimension, in meaning, so what's the expected dimension of my variety now? So it's the minimum between the dimension of the ambient space, okay, because if it reaches the ambient space, there's nothing to do. So it's the minimum between the dimension of the ambient space and the number of parameters minus the dimension of the gauge subgroup, okay? But if you just think of this, you're not taking care of two important facts. So first of all, it could exist some stabilizer of that group that reduce now the dimension that you have to count when you subtract the dimension of the gauge subgroup. And there could be something more in the fiber. The fact that you have found the gauge subgroup doesn't mean that's the only thing in the fiber.
So it's not even an upper bound or an lower bound.
Right, okay.
Why is it the expected?
because they do many, I mean, it's true in many cases. Okay, so the theorem that we will see later, it's true in many cases, and in many cases that they compute it, it's true. Okay, so but still, I mean, just as a very preliminary consideration, you have to take care of these two other facts, right? So I mean, if you want to formulate a precise theorem, just with the information that we have now, you have to say that it's the minimum between the dimension of the ambient space and the dimension of the parameter space minus the dimension of the gauge subgroup minus the dimension of the stabilizer, and it would be nice to know this dimension. And then you have to put a minor or equal here because there could be something more in the fiber that you don't know. So we have this very nice result of many people that passed from here. So that the dimension of the stabilizer is 0 in most cases. I'm not writing here the theorem. They have a very nice theorem where they perform many cases where the stabilizer is 0. And one important fact is that the stabilizer is 0 in 2 important cases for tensor network varieties. So if gamma is a cycle, so like a matrix product state, or if gamma is a grid, like PEPs. Okay, so in these 2 cases, there's no stabilizer. So you have to take care eventually only if there's something more in the fiber. The stabilizer is not causing any problem to you. These are the 2 theorems that I quoted already before. So this is for matrix product state with what's called the open boundary condition. And so here is the result. This is what exactly you expected. So the minimum between the ambient space and the parameter space minus the gauge subgroup. And I also computed this dimension for the tensor train, and this is the hierarchical Tucker when you have a perfect binary tree. Okay, and also there you have the expected dimension.
Open boundary means without the loop. Or with the loop.
When the 2
okay, without the loop.
Without the loop, yes. When the 2 are 1,
yeah.
when the 2 there are 1.
Okay.
And so what we could see is that, so for supercritical cases, for the case of supercritical, we don't have, I mean, with no other overabundant bond dimension, we were not able to improve like the statement that I already said. So we really don't see neither if there's something in the fiber, nor we were not able even to compute the stabilizer, but we were able to study better the case of the supercritical case. So for this supercritical case, the bound that we gave is sharp, and the dimension of the stabilizer is 0. So for the graph where you have supercritical vertices and that's it, you have the stabilizer is 0. And also this bound is really sharp. So it's attained. And then I would like to conclude with some example where there's something in the fiber. So here we did these 2 cases. So the triangle and the square. We fixed all the bond dimensions being 2. Okay. And we changed the physical dimensions. So these upper bounds are the bounds that you compute if you assume that there's nothing in the fiber. Okay, these upper bound and these upper bounds, and then you may compute the dimension of those variety. And it turns out that, for example, in this case, this is the smallest one, but there are other cases, those that I picked with the star. The dimension is not exactly the one that you expect from the upper bound. So there are cases where there is something more in the fiber. So in this case, you have something, you have like drop dimension 2, here you have drop dimension 3, and so on.
So lower bound is calculated.
It's exact.
Exactly.
It's not lower bound.
It's the actual.
It's the dimension of the, yeah. So I have to say that when I've seen this as a mathematician, I was very surprised because, I mean, it's nice to see that there are exceptions, and it's nice to see why there are exceptions and if there's a geometrical pattern. But when I went to physicists to say, oh, you know, there's something more than the gauge, you know? And then they say, oh, well, there's more than the gauge? And then I said, oh, you're losing 2 parameters when you're doing that. And then they say, okay, so what? I mean, these dimensions are small, but of course, when you work with like huge tensor network varieties, and you tell them that they are using 2 more parameters than needed, I mean, there's no point for them to change their whole architecture of all the algorithm that they already have developed for that number of parameters just to gain 2, right? So from my perspective, it will be interesting to see if this phenomenon can kind of grow, right? If there's some pattern that allows this dimension to enlarge. So as an example for this talk, I tell you why there is this dropping of 2 in this example here. So this is the triangle, all bond dimension being 2, and the physical dimensions are 2, 3, and 4. Okay. So your graph state is inside C2 times C2 3 times. And then the tensor network variety sits inside the projective space of the tensor product of the physical dimensions, so C2, C3, C4. So now take any tensor in here, okay, and consider the first flattening, the flattening that distinguishes the first vector space against the other. So you're sending a C2 into here. So the image of this tensor, whatever it is, it's either a line or a point. There's no other solution, okay? C2. Okay. Good. Now you may see that if instead of picking any tensor, you pick a tensor into the tensor network variety, what had happened to this flattening is that either the rank is 1, so you get a point, or you get a line, but a specific line, a line that intersects a set of matrices of rank at most 2 in 2 points. So it's not any line. It's every time you pick a tensor here, either you get a point or you get a line that intersects the matrices of rank at most 2 in 2 points. And these are these 2 points that drop you the dimension by 2. Because you count parameters, and parameters are 24, but then you impose the condition of passing through 1 point, you drop 1 dimension, through another point, you drop another dimension. 2 points count to the multiplicity, okay? And so, I mean, there's this dimension of dropping of 2. So this is what there's more in the fiber in that case.
So what's that? Well, yeah, where does that come from?
So I mean, that's our preliminary result, I would say. So I think it would be very interesting to keep. I mean, that was our first analysis. But so yes, why then? Is it true that if you, I mean, here you have rank, I mean, you have C2, and then here you have. Of course, here you have C3 and C4, so you may have rank 3 matrices here. So rank 2 is a variety in there, right? So if I increase this this dimension, I have higher rank matrices, for example. So does this always happen? I don't know. I mean, we are still here, right? That's really our point where we arrive. But I agree. That's the next step. To see if this geometrical pattern has, I mean, if there's some geometrical pattern in that. I'm almost.
But even for this, there's no short reasons. There's no like intuition.
I mean, I don't have an intuition because the other cases are different, for example. So there are different phenomena in the other cases. So maybe there's some more. So I just conclude with some further question. I mean, as you see, classify all subcritical cases, okay, where the upper bound is not reached. So y is not reached. And this was the question posed yesterday, but that is, so which is the smallest time such that the tensor belongs to it. But in another, you may rephrase it saying, pick instead of the given one, you may ask for an easier question, pick a generical one, a generic tensor. So which is the first tensor network variety that get it, that's equivalent to say, which is the first tensor network variety that fills the ambient space. Okay. So that's an easier question rather than the given one, which is the generic one. So yes, these are already other observations that were already done in this workshop, so that the gamma can be reasonably chosen from the context that you have, and so you may just wondering to decrease the ends. And this is something that I've always heard in this kind of talks, but I have to say that I don't know why. So I always heard that state of physical interest, like the ground state, they can always be represented by tensor network with very small n. Okay, good, but I don't know why this is true. And so this is more involved. So there are very well established procedures to find a good enough approximation of a tensor on a given tensor network. And all this, I mean, the ones that I think they use more, they're mainly local, so meaning that they approximate on a local vertex, one vertex per time. But so we tried with a student of mine, I mean the same student here, Claudia Lateri, to look for some more global algorithm, because if you're able to improve the dimension, really not just by 2, but by something interesting, then really what you can do when you have your parameterization, instead of taking the whole parameter space, you may slice the parameter space, right? And already slicing the parameter space by a linear space that has codimension equal to the dimension of the fiber, what you get is it's a finite number of points for every tensor network, right? And that's reduce the number of parameters. But for do this, you need to have a global algorithm then to approximate your tensor on the tensor network variety. A local algorithm is not working anymore because you lose all your structure if you slice with a linear space in the parameter space. Okay, so now there are very good local algorithms. So do there exist some global algorithm that good enough to replace the local algorithms? And if yes, then all these techniques of dimension may apply in a way. Okay, I think that this was everything I have to say.
Thank you. Questions?
It has a drop. Do you know whether the drop somehow grows?
Yeah, so we tried to do with this. We start with a very small one. So we try to add, like, to this triangle another triangle, for example. But that's tricky. So we did many examples, and then apparently, so the example that I did had this 2, 2, 2 here, and it was like 2, 3, 4, and the next one was 2, 4, 4. Okay, so if you lose all 2s, like if you lose also this one, then no. So if here I put a 3. Now the dimension is correct. If I add to this some other triangle by touching this vertex where I have a 2, then I lose this property of having something more in the fiber. So apparently this 2 is kind of important, the 2 here. So if I add some triangle here where I have other dimension, then yes, I get something more in the fiber. But if I touch these 2, I lose this property. So I mean that was my first idea. So why don't like propagating this, right? But apparently there is really something deep into this, some geometrical reason why I can propagate only in one direction.
Have you found any structure without 2?
Sorry?
Have you found any structure without 2?
So, no.
But that's also bounded by your computations, right?
Yeah.
Or not?
Yes. I mean, and I don't know how many of you are familiar with secant varieties, but if you transpose all this in the secant word, there is this very similarity that secant varieties of sacred variety, for example, are defective in many cases when you have P1s. So the P1s are always, when you have copies of P1s, you get a lot of defectiveness, right? And maybe there's a connection. I mean, for me, it's really a wide place where to look for many open questions. Yeah. There was another question.
Yeah, so does it matter here that we are over the complex field or it is a marginal?
That's a very difficult question for me. So I don't know what happens over the real. Probably it's even worse. I mean, at least for for tensor rank, when you go to the real, it's much more complicated than the spectrum. Like think to the generic, what we call the generic tensor rank. So for complex numbers, it's unique. It's the smallest secant variety that fills the ambient space. But that definition is not even well posed if you are in the real numbers, because you have many open set and none of them fills the ambient space. But as soon as they are open, they are good enough to be called generic. Indeed, they say typical ranks, and they have more typical ranks over the reals. And so, I mean, over the real numbers is really a more complicated setting. And I have no clue. I've never tried this over the reals. Because I think that physicists are interested over the complex numbers, right? I mean, for them, quantum is really complex.
Yeah.
Yeah.
You could even do finite fields, then you really lose it.
Yeah.
But you could compute it more easily. That is maybe also true. Right? If you want to do these kinds
just do
of
computations.
the finite like these, right? You want to know what are the exact values. I guess over finite fields should be probably easier.
Yeah.
To get some intuition, maybe. I do wonder if you get the same numbers. I mean, the finite fields will approximate. Like, is there potential for these gaps to grow much? Can they really grow much? Can they grow with the dimension? Yeah.
I hope that there's some point where I see some big gap.
Yeah.
I mean, I really don't know. I mean, for me, it's really, this is my very first result in this thing.
Is there a simple example of non-trivial stabilizer? It would be nice to
Yeah,
see
I don't
it.
know. How was it last week?
Yeah.
Is there an interpretation, like a physical interpretation for the stabilizer, because it's some parameterization, right? So it's a stabilizer of the parameterization, right?
Mm-hmm.
So can it be if we take a parameterization with a physical, build it from something physical, can the theorem that you showed, the connection, the sharpness, can tell us something about that what we're interested in?
So, I mean, that's the stabilizer of the gauge subgroup. So, I don't know. I mean, I don't know the physical.
Questions? All right. Thanks again.
Thank you.